It has been said, and I think safely can continue to be said, that we live in a scientific age. While no scientist has risen to the level of celebrity once occupied by Albert Einstein, there are several who are well enough known to be household names, and whose endorsements merit serious consideration by those who engage in the public square. One need only think of figures like Bill Nye, Neil deGrasse Tyson, and the recently passed Stephen Hawking to recognize that scientists have a certain cachet. The preeminence of science, however, warranted or not, is not limited to a few personalities. Advertisers know that if they can assert a scientific basis for their claims about whatever product they are trying to get us to buy, they have a much better chance of convincing us to do so. So too, in the various rhetorical arenas where science is often used to bolster arguments and win over opponents. Those who reject such scientific approaches are often ridiculed or worse. One of our podcast colleagues, a podcast known as Science Versus, uses a format wherein the host, the excellent Wendy Zuckerman, says something like, "There's this claim, but then there's science," followed by what sounds something like an epiphanal chorus of angelic voices suggesting that it is science, and perhaps science alone, that can and will deliver us from superstition and ignorance. With this emphasis on, and perhaps glorification of, science as a process of inquiry, however, comes a number of other questions. Aside from the very relevant concern of whether science is always the best method of investigating things, one must ask whether the knowledge that science claims to produce is truly reliable. Moreover, if science is now either the most dominant or the most esteemed form of inquiry in our broad society, are the tools it uses as valid as we think they are? How certain can we be of the knowledge science creates? To answer some of these questions, we must turn to a branch of philosophy devoted to understanding the nature of knowledge and how it is produced, epistemology. And in doing so, we must consider the work of one philosopher who, writing at the end of the scientific revolution and the beginning of the Enlightenment, wondered if the natural laws, becoming so prominent in the thinking of not only the physicists and astronomers, but also the philosophers in England, Europe, and North America who thought about politics, economics, and societies, were as certain as they all seemed to believe. What was the basis for scientific knowledge, he wondered. His answer has become an enduring thorn in the side of those who wish to claim absolute scientific credibility. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 4, Science and Certainty. Episode 1, The Problem of Induction. So here we are, at the beginning of a short mini-series devoted to some of the questions asked in the sub-discipline of philosophy known as the philosophy of science. This is going to be a bit different than our last two series that focused on the history of science with philosophical issues brought in when and where needed. This time, it's sort of going to be the other way around, where we'll look at various philosophical issues related to science, and we'll introduce them in a sort of historical context before really diving deeply into what they mean and seeing where they take us. In a sense, you can think of this as being on shore leave and going down to the local coffee house or pub, depending on the time period and personal preference, and sitting down with a few other explorers and spending some time chewing over the implications of what you've seen and learned over these last few voyages. For those itching to get back on the water, we'll get there soon enough, But while we repair and resupply, and the navigator pores over the various charts to get a sense of where the Odyssey will head next, this is a chance to put some of what you've learned into a broad context. Another thing we should say here, we're not real philosophers in any professional sense around here. Podcaster Dan Carlin likes to say he's a fan of history. Well, we here at the Scientific Odyssey are fans of philosophy. As such, we're going to try to bring you the relevant ideas as best we can as we've learned them from the various writers and thinkers, but we're bound to miss something or another. We'll try to avoid the worst omissions and errors by checking with a few professional philosophers that we know, but it's pretty likely we'll mess things up from time to time. For this, we apologize in advance, and if there's something you'd like to bring to our attention, please feel free to do so. Additionally, sometimes philosophy isn't everyone's cup of tea, if you know what I mean. We get that here, but we also feel that it's a really important type of inquiry to engage in. One of the great things about philosophy is that it tends to ask the really fundamental questions about things like knowledge and ethics and metaphysics, questions that sometimes practitioners of various other types of inquiry can gloss over or not delve deeply enough into. In this present endeavor, it will sometimes seem like philosophers are better at asking questions than they are at answering them. Again, while there is an understandable frustration in this, it's also a misleading one. Just because a question doesn't have a clear-cut and memorizable answer doesn't mean that considering what people throughout history have thought in relation to it doesn't teach us things. The attempts of philosophers to make progress on these various questions, in our case, those specifically related to the nature and practice of scientific inquiry, as well as the types of things scientists try to study, can reveal a great deal about the process and the best ways in which it can be conducted. So, if things sometimes seem to veer into the realm of counting angels on the head of a pin or alternatively trying to conceptualize the sound of one hand clapping, hang in there and we'll work to see if we can tie things back to more relatable applications before we get too deep into the weeds. So, are you still with us? Okay, fantastic. Let's try to talk about what's known as the problem of induction. And if we're going to talk about the problem of induction, we need to start by talking about what induction actually is. Now, this is something we actually covered somewhat in our first series, but if you haven't listened to that or it's been a while, let's do a little bit of a recap. There are two related ways to look at induction. One is through rhetoric or argumentation, and the other is through what I would guess call a process. These are related to each other in how they work to try to arrive at knowledge, and so let's see if we can sit down and take them in order to get an understanding. In the first case, we have what is known as inductive reasoning. The best way to talk about this is to contrast it with deductive reasoning. In deductive reasoning, the truth of whatever conclusion is reached is said to be inherent in the statements or premises used to reach that conclusion. This is a form of reasoning used in most mathematics and is usually exemplified by a statement that goes something like, if A equals B and B equals C, then, well, as probably everybody knows, A equals C. If the two initial statements, premises, are correct, A equals B and B equals C, then the conclusion that A equals C must be correct. Outside of mathematics, the premises are usually a bit more relatable than some abstract thing like A and B. The classic example of this that you find in all of the textbooks is something like premise A, all men are mortal. Premise B, Socrates was a man. Conclusion, Socrates was mortal. If A and B are true, then the conclusion, Socrates was immortal, absolutely has to be true. It cannot be false. That's the characteristic of a valid deductive argument. This is why in rhetoric you actually can't counter a deductive argument by attacking the conclusion. What you really have to do is question the premises. Maybe you argue that it's possible that Socrates wasn't a man, but rather some sort of a time-traveling cyborg former governor of California that traveled back in time to ancient Athens to argue against democratic principles or something like that. Who knows? In all deductive systems of reasoning, there are always some set of fundamental assumptions. Sometimes, as in the case of mathematics, these assumptions, usually known as axioms, are made to describe some mathematical state of things, some sort of system of self-consistent and non-contradictory things. But once those axioms are stated, they're always held to be true. And then what mathematicians will try to do is work out all of the true statements that can be derived from them about the system that they're trying to study. It should be noted, though, as sort of a callback to our previous series, that it was Einstein's colleague, Gödel, at the Institute of Advanced Studies who claimed that such frameworks will always have some amount of information that is left incomplete. By the way, if it seems like we're taking a lot of time to talk about deductive reasoning when we're really interested in inductive reasoning, it's because we'll return to this idea of deductive reasoning a bit later on in the series. So I want to make sure we sort of get that out there, kind of put a pin in that, put that on the back burner, whatever metaphor you want to use, because we are going to pull that idea back out and use it later on in a later episode. So, what's the deal with inductive reasoning? Well, with inductive reasoning, we make arguments wherein you may have cases where even when the premises of an argument might be true, the conclusion could still be false. An example here might be something like this. Premise A: most men in ancient Greece were taller than 5 feet. Premise B: Plato was a man. Conclusion: Plato was taller than 5 feet. Now, as you can see, there is now a certain level of uncertainty that creeps into the argument. Yes, most men were taller than 5 feet, but what if Plato was one of those guys who wasn't? That's actually possible. In this case, both the premises are true, but the conclusion still could be false. Now, there are a lot of ways to try and deal with this, but the most common, at least since the development of the branch of mathematics we call statistics, has to do with, you sort of work in probability. In this case, we try to quantify what we mean when we say most, quote unquote, most men are taller than 5 feet. If that number was, say, 60%, then we have a pretty good sense that there will be a lot of exceptions and that we shouldn't place much stock in the argument. If the number instead was, say, 98% of the men of Athens were taller than 5 feet, well, we can probably feel pretty good about the truth of our conclusion. Now, there are two things we want to say about this before we move on. The first is that when we're making arguments, we usually do this by making a chain of reasoning statements where the conclusion of one statement becomes a premise or part of the premises of the next statement. If that next step absolutely requires the previous conclusion to be true, well, an inductive argument might not actually cut it. If there are argument chains where there are multiple levels of inductive reasoning, the uncertainties of each level must be combined so that even if each individual step has a high probability of being true, the final conclusion of the overall argument might actually have a higher likelihood of being false than it does of being true. The second thing to note here is that very frequently, inductive reasoning arguments will argue from a general observation to a specific application. From most men, in the case of our argument, to specifically Plato, general to specific. As we will see in science, the application of previously established natural laws to specific instances will follow this same pattern. If I were to ask you what will happen when you drop a ball from a height of 5 meters in a building in, say, a small Kansas town you've never been to, you probably answer in a way that was consistent with whatever knowledge you've acquired by observing other falling bodies. If you've been listening to this podcast or have taken a physics class at some point, you probably use inductive reasoning to say something like, well, the law of falling bodies says that smooth, dense objects released near the surface of the Earth fall with a particular type of constantly accelerated motion. The sphere that will be dropped in Kansas is probably a small, dense object, therefore it will fall with a constantly accelerated motion. This is an inductive argument because in certain cases with certain types of spheres, say ping pong balls, the motion isn't constantly accelerating when they fall. This is the case whether we happen to know it or not, and so there's a chance that the ball in Kansas won't actually obey the law of falling bodies as we might expect it to through our use of inductive reasoning. Okay. Finally, we need to talk about the other meaning of induction, and that's the type of induction Aristotle talks about in conjunction with empirical acquisition of knowledge. Empirical knowledge is stuff we learn about the world around us through the use of our senses. Aristotle says that if we're clever, we can gather this knowledge and use it to arrive at an understanding of the physical universe. In many cases, this knowledge and understanding will be such that we'll be able to or led to make generalizations about the way things work in nature. We can say that when water in a container is placed over a fire, it will eventually boil and then evaporate. We make this generalization because we've seen such an event on a few occasions in somewhat different circumstances, and so we come to believe that this is the general occurrence in those circumstances. In this sense, induction is used to work from the specific case or cases to a general principle, or later, during the scientific revolution, something that might be called a natural law. Now, an important thing to understand is that this general principle is thought to apply both in space, i.e., it works everywhere, as stated in Newton's principle of universality, but also across different times. In other words, if various natural laws or principles have worked in the past, it's assumed that they'll work the same way in the future. This will be important as we move to talk about the various statements of the problem of induction. Finally, before we wrap up this section on explaining induction, let me acknowledge that this all can be just a bit abstract. The truth is that we all use induction every day. It's kind of like that, there was a TV show that said we all use math every day. Well, same thing here. We all use induction every day. Let's take a really concrete example to understand this. I'm guessing that almost everyone who is listening to this has driven a car. In fact, you might be driving one right now. Imagine getting into a car that you've never seen before and having to drive it. Maybe, it's something where you've rented the car at the airport for a business trip or something like that. And so, you walk out into the lot and here's this car that you've never seen before, you've never driven, and now you have to get into that car and drive it. Now, when you get into the car, I'm guessing you already know how to drive it, or I should say more specifically, how to steer the car. You know that the gas pedal's on the right, the brakes on the left if it's an automatic. You know that turning the steering wheel to the right means the car is going to turn to the right. And if you want to go to the left, well, you turn the wheel to the left. So how do you know this? Well, you know it through induction. If I think about it, I've probably driven about 36 different cars in my lifetime, give or take. Maybe a few more, maybe a few less, I don't know. I haven't actually really ever counted it up, but that seems like a pretty reasonable assumption. The car I learned to drive in, an old Toyota Corolla, worked that way, and so has every car, truck, moving van, etc. I've driven since. Based on that first experience or two, I generalized that the pedals were arranged in a certain way and the steering wheel worked in a certain way, and I've gone with that ever since. The more often that works, the more likely I am to think it will work every single time in the future. This is known as, in the fancy terms, enumerative induction. And I'm guessing probably the same is true for you. By the way, when you get to the other system controls for the car, you often find that they don't follow this sort of inductive rule, i.e., the turn controls might not be in the same place between two different cars, or the gas cap cover might not be on the same side of the car, so you're always driving around the gas pump islands trying to figure out where to park so you know how to put gas in the car. And so what you have to do is you have to take time to get acquainted with the car and struggle to operate that car properly. Move to a new car, maybe you have to learn a bunch of that stuff again. So in this example, we can see that induction is a huge thing that we use to get around the world every day, both literally and figuratively. Now, for those of you who are thinking, wait, isn't the reason the car's steering and propulsion controls all work the same is because there's some sort of industry standard? And, if you're thinking that, you're absolutely correct. That's an idea that we'll sort of talk about in a later show, and it has to do with the fact that there are other kinds of induction that we can sort of work with. However, the thing that's kind of interesting here is, even if that's the case, there's always the possibility that some, nefarious mechanic has switched the mechanical linkages in the hopes of creating some sort of carnage. Our faith in the operation of a vehicle is, at least in part, always due to our faith in inductively arrived at knowledge. And what we want to do after the break is sort of think about, is that faith justified? So, hopefully now that we have a better grasp of induction and how we tend to use it to acquire new knowledge that then we can use to understand the world, what's this so-called problem of induction? In philosophical terms, the problem of induction is a problem in the subfield of epistemology that is concerned with the nature of knowledge. In short, it has to do with whether knowledge acquired by means of inductive methods might be, as the Scottish philosopher David Hume might say, rationally believed or held to be true in some rational way. While Hume is probably the most important figure when it comes to stating the problem in its fullest extent, at least in what might be thought of as the early modern period, he's by no means the first to raise the question. In fact, the question about whether induction is trustworthy in producing knowledge goes about as far back as we have philosophy, even if we don't always have a good record of various schools of philosophical thought and their writings on the subject. One of the difficulties about much of classical philosophy is that unless the writings of a lesser-known philosopher was preserved in the work of a more significant figure, such as Plato or an Aristotle, their work usually didn't make it through the thin neck of the hourglass that represents the fall of the Western Roman Empire, and the dislocations and disruptions that calamity and the events surrounded it produced. This means that there is occasionally some complexity in who said what and when, and who it might have later influenced when it comes to the development of science as a method of inquiry. Nowhere is this better illustrated, I think, than in the case of the Roman philosopher known as Sextus Empiricus. What we know about him is that he was a Roman philosopher probably in the period of the 5 good emperors between roughly 100 and 200 CE, who was associated with the empirical school of medicine during that period. He was also a student and teacher of Greek philosophy, specifically associated with the school of skepticism known as Pyrrhonism, after its founder Pyrrho, that dated back to probably somewhere around the 4th century BCE. One of the tenets of the skeptical philosophical school in general, and Pyrrhonian thinking specifically, was to question the validity of various types and sources of knowledge, including both deductive and inductive knowledge. Empiricus wrote a treatise for his fellow Romans who were interested in Greek philosophy titled Outlines of Pyrrhonism, wherein he called into question whether knowledge arrived at through inductive means could really be thought of as having universal validity. Writing to sort of the proponents of induction and, in light of their arguments in favor of it, he says, quote, "When they propose to establish the universal from the particulars by means of induction, they will effect this by a review either all or some of the particulars. But if they review some, the induction will be insecure, since some of the particulars omitted in the induction may contravene the universal. While, if they are to review all, they will be toiling at the impossible, since the particulars are infinite and indefinite." End quote. Arguments such as these may have contributed to the abandonment by much of the classical world of Aristotle's induction and empiricism in favor of the more deductive and rationalist approach of Plato. Ironically, Empiricus's work would be lost to medieval Europe for centuries until several manuscripts migrated from the Byzantine East to libraries in Renaissance Italy and then were translated into Latin in the early 16th century. Europe, now recovering from centuries of struggle and having established a variety of institutions willing to consider skepticism, would find much of Empiricus's writings to think about and discuss. As such, his works would have a profound influence on philosophers like Hume. In the Eastern Roman and Byzantine empires, while the intellectual culture would not be favorable towards skepticism, with a number of works written during the medieval period to refute those conclusions, the idea of questioning knowledge and its sources would be transmitted into Arabic and Islamic culture and find their way into the writing of the various hakim and scholars of the time. Ibn Sina, or as he was known in Europe, Avicenna, would in the early 10th century ask how a scientist would arrive at, quote, "the initial axioms or hypotheses of a deductive science without inferring them from some more basic premises," end quote. His answer was a combination of both Aristotelian induction and an early form of an experimental method to arrive at a, quote, "relation that holds between the terms which would allow for absolute universal certainty," end quote. He was, however, uncertain of the process of induction, writing that it, quote, does not lead to the absolute, universal, and certain premises it purports to provide, end quote. Roughly 50 years after the work of Ibn Sina, the early physicist Ibn al-Haytham would also embrace skepticism as a fundamental tool of inquiry when he wrote in his book of optics, quote, the duty of the man who investigates the writings of the scientist, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into prejudice or leniency, end quote. Finally, the Carvaka school of Indian philosophy, which, existed at roughly this same time period, would also question whether inductive inference could be used to justify knowledge on the basis of whether it was able to establish a connection between a preceding thing and what followed that preceding thing, what we might call cause and effect here in the West. While it seems unlikely that Hume was aware of these ideas, it would turn out that his approach to the problem in part would follow many of the same paths. So, as can be seen, the idea that induction can produce knowledge that is as certain as deduction was actually, an idea of some debate among most of the cultures that tried to ascertain whether inductive knowledge, or whether the knowledge that they were obtaining and using was actually valid and reliable. So, at long last, this brings us to the work of David Hume and what is usually thought of as the modern formulation for the problem of induction. Before we proceed, I should say that what follows is really just a very brief sketch of his ideas, along with a few examples. There are, of course, much more exhaustive discussions at both the Stanford Encyclopedia of Philosophy as well as on the Internet Encyclopedia of Philosophy, both of which include a vast number of sources for the interested listener to follow up with. Probably the best source of all of those things, if you want to wade through it, is, of course, Hume's own writing on the topic. So, a bit of biographical information on Hume. He was a Scottish philosopher, among other things, who lived and wrote in the mid-1700s as part of what is commonly known as the Scottish Enlightenment. His work in philosophy covered a wide number of areas and was grounded in the framework of British empiricism, which can be said to have begun with Francis Bacon and Thomas Hobbes and continued through him and his contemporaries such as George Berkeley. In a scientific sense, he would have been a contemporary of Voltaire, Halley, and Huygens for the most part, as well as some of the early pneumatic chemists such as Joseph Black. Philosophically, he was the key figure writing in response to Cartesian rationalism and dualism, and he raised a number of objections to those approaches to various questions in philosophy. His work in the field of philosophy of knowledge or epistemology is summed up in two pieces of writing: a treatise on human nature and an inquiry concerning human understanding. In both, he sets forth his ideas on knowledge based on his, what we could call an axiomatic statement known as the copy principle. In this, he says that all thoughts we have are based on what we experience. These thoughts can be divided into ideas and impressions, with the first originating in the intellect of a person, while the second comes from our senses, though they can be in the form of memory with respects to things that we've experienced in the past. Hume claims that impressions are more vivid than ideas, and thus ideas should be thought of as products of impressions, whether in the present or, more often, from the past, as we've stated previously. Additionally, he asserts that one doesn't have to have experienced the specific thing, say King Midas, to be able to imagine it. We can, though, through something he calls resemblance, we'll talk about that in a minute, sort of transfer our knowledge from one thing to another. Here it may be that through our experience with people in positions of authority, or our having seen or touched a golden object such as a ring, we can combine those two things using our imagination to create a composite or synthetic idea of a king who can turn things to gold if we read a story about such a figure, i.e. the mythological story of King Midas. If a person somehow had grown up in a totally egalitarian culture with no rulers that had an island or were on an island wherein there were only wooden objects that had ever been used, Hume would say that the person would have no way to engage the King Midas story in its traditional telling unless it were modified to be told in terms of what that person might have experienced in their own culture. Now, Hume then goes on to say that there are really two ways we associate ideas, either through what he calls natural relations or philosophical relations. For the purposes of what we're talking about here, we're going to focus on the former. Natural relations help or allow the imagination to connect ideas in one of three different ways: resemblance, contiguity, and cause and effect. I think the first two are probably pretty obvious. For resemblance, copper, and brass, and even bronze, when shined up real well, look a lot like gold, so the King Midas story would be accessible to someone who had experienced anything like those metals. The same would probably be true if one imagines a president as sort of being like a king, or maybe some other, leadership or ruler type of individual. Contiguity is similar in its ability to create an association with certainty. If you're living in a situation where you know of a person or figure whose greed destroys everything they touch, then the King Midas story makes a lot of sense. It's the third of these natural relations that Hume claims is less certain and most frequent. In cause and effect, you experience something, we'll call it A for the moment, and then experience a second thing, B, in close association with the first. Your mind, seeking understanding and pattern, likely as the evolutionary desire to be able to predict the future and whatever is going to occur in it, attempts to create a causal relationship between the two. To harken back to our early example, you turn the steering wheel to the right, that'd be thing A, and the car turns to the right, thing B. Your mind decides that turning the steering wheel in this vehicle in a direction might reliably cause the car to turn in that direction, the intended effect. If you test this out a few more times and it works in each case, your mind creates a cause and effect relationship. This relationship will then be used to predict not only the future behavior of that car, but perhaps of all other similar vehicles. One can see how this can be used to arrive at all sorts of descriptions of the behavior of natural systems through the creation of things like natural laws or theoretical frameworks. Now, to add another layer, if but briefly, to this picture of knowledge that Hume is developing. When he considers what he calls objects of knowledge, in other words, the things we claim to know to be true, he says that they can either be categorized into two types in something known as Hume's fork. They're either said to be relations of ideas or matters of fact. Relations of ideas are things like mathematics, say two parallel straight lines that never cross in Euclidean geometry, and then the things that we can deductively derive from that axiom. Relations of ideas will always be true if they are correctly developed from the predecessor ideas. Otherwise, there would be contradiction wherein we would say something like A is true and not A is also true, which you can't have with relations of ideas. The second of the two classifications from Hume's fork are things that we've been reliably observed to take place, i.e. experienced. When we get into the first car, we drive and turn the wheel to the left, and we experience the car going to the left. That whole experience is what we call a matter of fact in that instance, that a left-hand turn of the wheel is accompanied by a left-hand turn of the car. The same can be said for an observation of the motion of a falling ball in a given circumstance, or the data recorded of a planet's motions with respect to the background stars over the course of many nights. Because these are directly experienced through the use of the senses, Hume would say these are matters of fact and thus are beyond dispute if the reporter of the event is considered reliable, which is, by the way, something we're generally going to assume throughout the discussion. Trying to do something else just makes this a whole nother thing. So we're going to stay with good observers and working with what they reliably observe. Now, when one matter of fact is related to another matter of fact in Hume's schema, there will be actually the possibility of a contradictory relationship. Otherwise, we'd just be talking about relations of ideas. It is only through experience that we see what actually is because, as Hume says, it's always possible for something to be otherwise until it's directly observed. For example, we may never have seen human consciousness apart from its expression through a physical form. But we know that there are all sorts of literary devices that show the disembodied human spirit, whether those be ghosts in a horror movie or some sort of higher being, Star Trek elder kind of thing in a science fiction narrative. Thus, it's possible for us at least to consider a contradiction to the relationship that human consciousness and the human body, however constituted, are always found together and thus connected. So why is this matters of fact, relations of ideas distinction so important? Well, Hume says that all cause and effect relationships are to be placed in the category of being matters of fact, because they're only known through our direct experience, which means that it's always possible to imagine a given cause producing a different effect until we observe them in continuity, or, put another way, one right after the other. We spend a lot of our time making sense of the world through various cause and effect relationships that allow us to predict how various objects are going to interact and behave. Frequently, as in the case of steering a car, such matters of fact are in fact matters of life and death. Therefore, it behooves us to ask whether or not we are actually being reasonable in doing this. A good example of this kind of process that's a lot less life or death than driving a car in heavy traffic at rush hour or something like that is to think about what might happen on a billiards table in a typical billiards game. Say I use the cue stick to hit one ball towards another stationary ball so that it is clear that a straight-on collision between the two balls will take place. Now let's say we could freeze frame that for a moment, and I were to ask you what will happen as a result of the collision. Let's say I ask you that right before the collision happens, so you actually haven't seen it yet. And let's just say as an additional wrinkle, at least for just this moment, let's say you've never actually seen billiards or pool shot. And so as you think about it, you come up with a whole bunch of possible outcomes. Maybe the first ball could hit the second ball and stop while the first ball moves away from that collision in a straight line. Perhaps the first ball bounces back towards you while the second ball remains still, sort of ricochets off, It could be that the first ball stops and the second ball, rolls forward but faster or slower. Or maybe the first ball hops the second ball. There are all kinds of other possibilities, of course, but you kind of get the picture. In each case, you can imagine a possible outcome that might contradict your prediction of what will happen. So, how are you supposed to decide? How are you supposed to make a prediction? Now, Hume says that one way you might be able to do this is to use that resemblance we talked about earlier. Maybe as a child you played marbles in the school playground, and so your experience there might inform your prediction. You're going to say something like, these billiard balls, they seem to be round or spherical, and they're pretty hard like marbles, so whatever I kind of think happens on the, playing marbles on the playground will work here too. In doing this, you've inductively generalized your matter-of-fact experience from the playground to a new context. Or, now let's say we relax our earlier restriction that said you'd never seen this done, and maybe you've actually seen billiards played on TV. And so you can apply your experience from that in an inductive fashion to this case. You haven't actually played billiards, but you've seen other people do it. Or finally, of course, you might be, the absolute pool shark. You've played billiards all of your life, and so you have a ton of experience from that. In all of these cases, the only way you make a prediction on the behavior of the two balls after the collision is to draw on your previous matter-of-fact knowledge. In doing this, you will have developed a model of causation that relates the motion of the first ball going into the collision with the motion of the second ball coming out of it. The more experience you have with the system you're making a prediction about, either by similar or direct experience, the more confident you'll be in saying what will occur. The same will be true the more knowledge you have about the specifics of the system, i.e. things like, do both balls have the same mass? Do you understand the law of conservation of momentum? Any of those kinds of things. And this is the same thing that's going on for getting in a car you've never driven or seen anyone else drive. You draw on your previous experience to be able to predict how the car will respond to steering input. Note, though, that there may be cases where your previous experience might not work well, especially in having to transfer knowledge from one system to a similar but not exactly the same type of second system. For example, if you're flying an airplane, turning the steering wheel might not turn the plane right or left as it does with a car, but rather change the orientation of the plane's wings with the horizontal. In this case, the expected cause and effect relationship will not produce the predicted outcome, and so your knowledge would have been said to be false. This is one of the really difficult things, by the way, about extending natural laws in science from one specific type of system to a similar one. A great example of this is what's known as the ideal gas law. We've talked about it on the podcast before. If you took a chemistry class in high school or maybe college, you might remember that for certain types of gases, there's a relationship between a gas's pressure, volume, temperature, and number of particles, or sometimes called number of moles, and that relationship can be stated by the mathematical expression sometimes written as PV equals nRT. Now, this law is actually a combination of three simpler gas laws, and it works really well in predicting the behavior of certain types of gases, things like hydrogen, helium, oxygen, nitrogen, those sorts of things. So, given that success, you might think it'll work well for all gases, but it turns out that's not actually true. There are other gases, things like ammonia or methane, wherein the ideal gas law fails to accurately predict what will happen to the pressure of the gas in a container when the temperature of that gas is increased by a known amount. These quote-unquote non-ideal gases do not follow the inductively arrived at PV equals nRT relationship for reasons that, until an atomic theory of matter was fully developed in the 1830s and then applied to gases in a statistical fashion in the 1850s, remained a complete mystery. So, what Hume asks then is whether we're truly justified in doing this thing that we so often do in science, applying either inductive reasoning or Aristotle's process of induction to predict the future behavior of systems. And by justified, he means, can we reasonably, in other words, by using our sense of reason, believe that there's a 100% chance of the causal relationship holding true in every instance? Hume would say that in spite of the reality that all human beings use this process every day in a multitude of circumstances, we can't actually say that. He says that there will always be some uncertainty or improbability in our claim that will allow for a contradictory outcome. And this really is the problem of induction. Hume argues that induction cannot produce 100% reliable knowledge using two different kinds of arguments. To understand these, we must realize that given our previous discussion, Hume claims that the only way we develop models of cause and effect is through continuity of events, or what he calls constant conjunction. In other words, observing the association between event A and event B over and over and over again. Turn the steering wheel left, the car goes left. Do it in one car, do it in another car, do it in every car. What we don't directly observe in this is the cause. Cause can't be known beforehand or, a priori, to use the fancy term from logic. And thus it must be inferred through the conjunction that takes place over and over and over in our experience until we elevate it to, something like natural law. The first part of the problem is then, as Sextus Empiricus pointed out, is that unless we can observe every single possible occurrence of something, there's always a possibility that there's a counterexample to our causal relationship out there. Unless we can deductively prove that some cause will always lead to the same effect, we have a less than 100% certainty in our conclusion, and thus the knowledge arrived at in this way might turn out to be false in some set of circumstances. One of the prime examples often used to illustrate this has to do with swans. If we go all over Europe, for example, examining swans, and, when doing that, we find them all to be white. And so we could perhaps make the claim that all swans are white. The thing about this, though, is that if we're honest, we have to acknowledge that there are probably many places we haven't examined that may or may not have white swans. What's interesting is if, let's say, we go to North America and we look for swans, finding more white swans probably doesn't add much to the certainty of our conclusion. However, if we were to find even one non-white swan, then our inductively arrived at piece of knowledge that all swans are white would be immediately made false. We must acknowledge that such a discovery is possible even if we haven't made it yet, as there is no deductively arrived at reason or cause for swans to be white and only white, and we haven't looked in every conceivable location where swans might exist and seen only white ones. By the way, here's another place where we want to put a little pin in this example, as it will become important in a later episode in this series. The second part of the problem has to do with how we justify whether induction works to provide knowledge with any reliability at all. The way Hume says we do this is that we claim induction's always worked pretty well in the past, and so we can be assured that it will work well in making predictions going forward. This, however, is, as you can probably tell, an inductive argument. It's always worked before, right? There is no deductive reason that induction should work the same way in the future. So what we're really doing is using induction to prove induction, which Hume points out is either circular reasoning or begging the question, both of which are logical fallacies. In short, Hume's expression of the problem of induction, arising so soon after the work of Kepler, Galileo, and Newton's mathematization of philosophy in the form of natural laws, calls into question how reliable knowledge gained from those laws actually is. Given that science, as a process of inquiry, at least as described by men like Aristotle and much later Francis Bacon, is fundamentally inductive, can the knowledge it arrives at least be reasonably believed? I think Hume's answer would be, beyond matters of fact, things that you've empirically observed, the answer might just be no. And that's something we're going to have to take a deeper look into down the road. So, having stated the problem of induction in more or less its modern form, we need to see if there are ways to address it. We'll spend the next couple of episodes looking at the various responses and evaluating them to see what we can learn. One thing that I should point out is that there are more recent attempts to recast the problem in more general terms. The one I've come across most often is that put forward by the American philosopher Nelson Goodman in his 1983 book, Fact, Fiction, and Forecast, wherein he attempts to find criteria one might use to distinguish between observations that lend credence to establishing things like natural laws from those that may be thought of as being mere accidents or happenstance. We won't go down those very rabbit holes in this series, as we're only seeking an introduction to the problem and some of the ways Hume's successors, both in philosophy and science, have tried to resolve it. But for those of you who are interested or intrigued by the problem, that's another resource to go check out. Just a few things to mention here at the end of the episode. This week's shout out, in a completely non-scientific way, goes to the athletes who competed in the World Cup, and congratulations to the French national team, the Les Bleus. I'm a latecomer here to the beautiful game, and I have to say, over the last several weeks, I've really enjoyed watching these guys play. All honor and respect to the Croatian team that, even though they came up a little short in that last game, I don't think I've ever seen such a tenacious team. What an incredible effort by everybody involved. I also want to remind you that we're in the middle of our summer odyssey. If you've got stories of travel, adventure, discovery, or exploration that you want to tell, I hope you'll share them with us at our Facebook group. If you're not on the book, as it were, you can relate them to me by emailing me at celdavies@mac.com. You can find me at Twitter at Chad Davies, and I'll be happy to share them across our various forums. I'd love to show everybody what the crew of the Odyssey here is doing. For me, the big news is that I passed my 2-year checkup on my neck after the crash with flying colors. It's hard to believe that 24 months ago I was sitting in my recliner with a big neck brace after being run over by that semi-truck while trying to write episodes about the philosophy of time, but here we are. And I'm very, very thankful to be here and being able to continue the Odyssey with you all. I'm glad to have made a good recovery, and I want to say thanks to everyone who's been pulling for me near and far. Your kind words and encouragement have had a lot to do with me getting to this point. I do want to ask you all for a favor, one I've mentioned previously. If you know someone who you think might enjoy the podcast, won't you share it with them? We're always looking for more members of the crew, and the best way for us to find them is for you to let folks know about what we're doing. Of course, strong reviews at the various podcast distribution tools help out a lot, and we welcome them whenever you feel moved to write them, but nothing beats a word-of-mouth recommendation. So if you know a teacher or have a student, work with a fellow lover of science, history, or philosophy, or know another nerd or geek who digs learning about all things scientific, invite them to come join us as we travel across space and time. So I understand it, I think Comic-Con's coming up, and if you happen to be going to that, let some folks know about us. We'd really like to have the folks there find us. And for all of you who have already left us reviews, sent emails to friends, played the podcast in cars with others while traveling, or promoted the show in so many other ways, you have our everlasting gratitude. Until next time, full sails on your journey.